It was exactly a year ago that Yensup Lee, our speaker right before lunch, and was giving a talk bragging, like he did this last time, bragging about a new Sci-5 core. And I was sitting right there in the front row. And he was said, you know, it's got 4.9 core marks per gigahertz and 2.5 drystone MIPS per megahertz. And he says, I'm standing this in front of Dave Patterson, who really doesn't like drystone or core mark as benchmark. Sorry, this is the industrial standard I learned. And so that really pissed me off. So I was trying to figure out, you know, why did that piss me off so much? And drystone was invented 35 years ago. And when Hennessy and I wrote our textbook, we, you know, at the end of the chapters, we have this fallacies and pitfalls things. And one of the pitfalls was using synthetic programs to predict real performance. And so we put that in our first edition, and then we embraced the spec benchmark, which is a suite of programs, and the second and third edition. And by the third edition, the reviewers said, you know, you don't need that pitfall anymore. Nobody uses that, right? And so I think bringing into a modern analogy, it's like, I think of it like measles. I think of drystone like measles, right? It's like people invented vaccines. When I was a kid, you got vaccines. Nobody died of measles anymore, but there are these people who don't believe in vaccines, and now people are dying of measles again. So that's drystone. Drystone is the measles of computing. and I can't believe there's a community, the embedded community, that still quotes drystones. People modify their processors to make this 35-year-old silly program run better because that's what gets quoted. So that, the realization that that was shockingly still true in 2018 led to Embench. So it is a group of academics and industry that's developing this thing. And we, like the rest of RISC-V Foundation, would love your help. If you would like to help us with this, send us email to info@embench.org. It's free, like RISC-V is free, the benchmark is free. It's easy to port. It's designed to be, we only included programs that make that easy to do. Instead of having one synthetic program to try and predict real performance, it's a suite of about 20 small real programs. They're small because they're for embedded. And what we do, like spec, we calculate the geometric mean of those, kind of the average of those 20 programs rather than using a synthetic program. But we also novelly include a standard deviation. So you see how significant the differences are. Embedded really cares about code size because the size of the memory really matters in the cost of it, so we included that, as well as context switch times and interrupt latency, which we aspire to do. Surprisingly, they're novel for embedded computing, even though they're really important. Like RISC-V having a foundation to keep it going, we have joined the FOSSI Foundation, so we're a subcommittee of that, so that's why we can keep it free. We don't need to charge money for it. And like the MLPerf benchmarks, we're following this agile benchmark philosophy. We're going to bring out a 0.5 version, get feedback on that, make it better. We're stepwise refinement. So it doesn't have to be perfect at the front, and we'll eventually get there. But even at this kind of nascent state, we think this is probably going to be a contribution to embedded computing. Even this initial version is a lot better than what exists today. So here is what it is. If you can read this, there's about 20 programs. There's encryption, there's JPEG, there's compression, decompression, matrix multiply, sorts, things like that. The color coding on the far side is in red is high and green is low. So the one column is branch, so if it's branch intensive, one column is memory intensive, and one column is compute intensive. And there's turns out 5 in each of these categories, 5 compute intensive, 5 branch intensive, 5 memory intensive. So that's our suite. There's a GitHub website. You can download it right now. You can go to embench.iot and GitHub and get it, and other people have done that already. So what affects code size? First of all, the instruction set architecture. There's lots of them, but also the variations of the instruction set architecture we know. The compiler plays this really important role. And then not only the compiler, but what optimizations do you turn on? And those kind of questions are, well, how fast are compilers improving? Or is it like the older ISAs have much better compilers? And then the libraries that play an important role. We decided to exclude the libraries because since our programs are small, the libraries would kind of swamp that. So in practice, libraries are important, but we're going to keep that as a separate category. So let's start looking at results. So we're using the pulp RISC-V core. This is for the latest version of GCC. And what you see across the slide from left to right is what happens when you turn on optimizations. And this one we're talking about speed, where higher is faster. So if you want your compiler to go fast and don't spend any time optimizing, it hits performance by a factor of 2. 01 gets you to 0.9, 02 to 1.0. If you do 03, which takes longer, you get another 10%. You do a little bit of inlining, makes no difference. But if you do loop enrolling and inlining, inline procedure calls and lots of looping enrolling, you can get another 10% to be 1.2, use this metric. So that's the speed GCC versions. The size optimizations, the OS one, is it brings the performance drops from 1.2 to basically 0.9. And then if you do really dense things in terms of saving and restoring, that gets 0.9. So the M-save and N-restore optimization for RISC-V is to reduce code size at the entry and exit of every procedure is another procedure call that saves the registers erased and calls it back. So it's going to be extra procedure calls per procedure call, but it could take less space. So that should slow it down some. Okay, so there's RISC-V and GCC. We said we include standard deviations, and so I've shown to see the blue bars of standard deviations. You can see how much that varies. And if you look at 03 with inlining, there's a big variation in the speed. What about code size? Again, if you don't turn any optimizations, your programs are about twice as big. But if you do go overboard, or you want to get the highest performance possible with unrolling everything and inlining everything, your code size could triple to do that. And then what you can see with the save and restore, it goes from 1.05 to 0.98. So you get about 7 or 8% benefit from this M-save and restore trick. And again, this shows the variations. The blue bars shows the standard deviations, and that inlining can have very big programs. It could be within one standard deviation of a factor of 5. Okay, so some observations so far. The M-save restores reduces code size about 7%, but because of the extra procedure calls and returns, it can hurt performance about 10%. And then, in terms of putting benchmarks together, this is what we want to link code size and speed. Otherwise, you could be 1.2 times as fast and small, but really, if you're going to do all that inlining performance, your program's going to be a lot bigger, maybe 3 times as big. For a lot of embedded applications, they don't want that. So to get more realistic evaluation, you want to see performance and code size. And then RISC-V has these optional extensions. What's happened? Like multiply and divide are even optional. So that has a huge impact. This one's on performance. It goes from, it goes up by a factor of 1.5 or so without multiply and divide to having it. And then the C-clamp is compression. Compression doesn't affect performance, either optimizing for speed or the OS ones are optimizing for size. But adding multiply and divide has a big performance impact. And then here shows the standard deviations. And if you don't have the multiply and divide, it can be widely varying, very large standard deviations. In terms of code size, you actually multiply and divide having those instructions rather than doing it by the compiler saves a few percent in the procedure size. It's a few percent smaller. And then the compression makes this huge impact on the code size is what we could expect. And this shows the standard deviations, which are more modest in terms of code size. So kind of summarizing a couple of slides there, multiply and divide for the Embench 20 programs on average, and it speeds things up over just the integer base by factors 1.5 to 1.7. And surprisingly, to me, it reduces code size by a little bit, 3 to 6%. Compress doesn't hurt performance. I didn't expect it to, but it was nice to verify that, but reduces code size by a factor of 1.4 to 1.5. And then, depending if you're compiling for speed, the -02 versus compiling for size, you can get bigger impact benefits in terms of size for that. And if you just do the integer base, you can get widely varying performance because of how frequently you use multiply and divide. So this, thanks to my collaborator Jeremy Bennett, who's talking shortly, there's a lot of new results. One of the new results we got was to look at GCC performance over time. So at the bottom of the axis, I showed both the version of the compiler and the actual date that it was released. So the leftmost one is August of 2016, and the rightmost one is last month. So ARM in the blue bars went in terms of code size of 0.92, it got 1% better to 0.91, and it stays flat for the last 3 years. So starting RISC-V just a year ago, that first column with red, it was just almost exactly a year, December 2018, and RISC-V is at 1.02, and the version of today, it's down to 0.98. So that's a 4% improvement in code size in the last year for RISC-V. So for those of us who enjoy instruction sets, 4% doesn't seem like very much, but you have to do a lot of tricks to get 4% in code size, and that's per year. So I don't know if I can do a Moore's law and predict 4% improvement per year for the next several years, but if we can keep getting better, that's going to really close the gap. And presumably, ARM's been around, ARM v7's been around for a long time, so it's not surprising GCC isn't changing very fast. Let's look at different architectures. The Atmel AVR is a 8-bit microcontroller. The ARC is a 32-bit RISC processor. Unfortunately, Jeremy couldn't get the compressed instructions working, so it's not a fair comparison. There's RISC-V, and then the ARM M4 core, which is a very popular core, and as is the RISC-V, not as popular, but pretty popular in the RISC-V community. So what happens to code size? And so the leftmost one is the AVR, and again, on the left is compiling for speed, on the right is compiling for size. So you can see that it's a factor of 2 larger, that AVR microcontroller code, so it's not a very good code density. The ARC one, again, is misleading because we don't have the compressed instructions working, but you can see when you're compiling for speed, there's about a factor of 1.2 between RISC-V and ARM. If we compile for size using the msave mreturn, the gap is about 7% between RISC and ARM, and there's still this big factors on the left. And this shows the standard deviations, again, where AVR could be very large variations. The other ones are pretty stable. And this is of results of this morning I got from Jeremy and put on the slides. So this is the RISC-V option. This was not an option I was very excited about. But there are people who believed because there are processors with 16 registers instead of 32 registers, you couldn't ship a product with 32 registers. You had to have a version with 16 registers. So I was really interested to find out, well, just what's the impact of having 16 registers? This is, again, using the GCC compiler. And I circled the results in purple there. So what I'm comparing, this is the older versions of the slides. I think I didn't get the latest version of slides. Don't look at those slides. I wonder if I can blank the slides. I think I can blank slides. Okay, I will tell you what the results are. So since you're afraid of having 32 registers, you definitely don't want multiply and divide, right? You can't do that. I did.
Oh, intentionally?
Yes,
oh, okay, great. On
purpose, because what's on the slide isn't what I wanted you to see. Okay, and so the difference between, so let's compare just the base instruction set with compression to the, to the embedded version with compression. And the performance hit, as I remember, is about a factor of 1.3. I think that's right. So it's like a 30%, yeah, that's right. It's 33% slower if you go to 16 registers. The code size difference was 7%. So it was 7% larger programs by using 16 registers instead of 32. So for the people who advocated that we just had to have 16 register versions, the E version of it I don't know what they're going to think. Is a third slower and 7% bigger programs, but only 16 registers? Is that a good thing? I don't. It's not obvious to me. Come talk to me afterwards, or we can ask questions and see if that's true. Okay. So this is just the beginning. Embench is just starting to work. There's all kinds of things to explore. Lots of different compilers, lots more architectures, many processors to evaluate when we get into the performance. We haven't included the context switch times. We know how to measure that RISC-V. We need some help for the other architectures. We want to get to interrupt latency and floating point. And again, and then collect and publish results. We just got the beginnings of that. We could need some help. So once again, like the RISC-V culture, please, if you're interested in helping, send us email at info@embench.org. So now there's 2 talks by people who have been helping. One by Nidal Four and Ofer Shinar. In the next session, they're going to be in 220C, which is around the corner, and then Jeremy's going to talk after that. Both of them are going to be talking about compilers and architectures. The Western Digital folk are going to be using test cases from real scenarios. Jeremy's going to use Embench and look at other compilers and other, like the bit extensions. Okay, with that, so code size and performance, my conclusions, we tried linking them. It seems like that made the case. The M instruction is multiply and divide are really good things in terms of performance and even benefits code size. RISC-V is a lot smaller, and ARM are a lot smaller than this old microcontroller. And Thumb is smaller, it's within 1 standard deviation, and actually the gap is closing as the GCC compiler has gotten better like it has in this last year. From an instruction set perspective, the loads multiple, store multiple, probably you could get the same code size without the M7 Torrent. You could get maybe a 10% performance benefit. The implementation is more complicated, but that's pretty clearly what's going on. We think Embench is already an improvement, and we're looking forward to, I guess I'll give some kind of award, like a signed textbook to the first presentation who quotes Embench at the RISC-V Summit. Okay, with that, I have time for questions, and there are microphones, and I want to be the first person to actually get a question at the RISC-V Summit. Okay, there's a question. I'll repeat it. What was the compiler we used for ARM? Yeah, so this study is all using GCC. So as I mentioned, there's lots of different compilers there, and it would be really interesting to use proprietary compilers and ARMS compilers to see what the difference is. There's a likely fellow. I think I heard it.
Okay, there we go. So I noticed that some of the programs in the list have a total code size of just a few hundred bytes. Are you not a bit concerned that that could make it easier to game or could skew the results from relatively small changes?
Yeah, so when we got started on this, inspired by this measles outbreak, and I can't believe that into 2019 we still have measles in computer benchmarking, we thought we were going to have to invent a bunch of benchmarks. In terms of outreach, with Jeremy Bennett, there's this Beebs benchmarks that have already been ported. They are small programs. And so, but part of the kind of the benchmarking philosophy is if you have a suite of programs, well, first of all, benchmarking philosophy, people will do targeted efforts against benchmarks, right? And the smaller the program, the greater the chance that they will do that. These have been around for a few years, and the Beebs isn't maybe as popular as Embench I hope will be. But if it does get targeted and broken, if you have a suite of programs, what you do is you throw those out and replace them with new ones. We expect to be doing that. The problem is with something like Drystone is it's fixed for 35 years, right? And when it gets targeted, what do you do, right? So that's kind of built into the philosophy of Embench. Other questions? Yes? How does cache capacity? Well, I'm kind of new to the embedded world, but apparently pretty normally what happens is you expect everything to be in caches. And so these things have iteration loops. I think they run for about 4 seconds, all of them with different iterations. So it's almost always 100% cache hit mates, but that apparently is typical for the embedded computing. So you wouldn't expect to be cache misses here. Another question? You're gonna have to shout. Vector instructions? That's probably a good question for Jeremy. I could probably, I'll go back to get the list of programs. Our intent is to, I know what we will do is in a future version, we will do a floating point version of these things. And when you get to floating point, there's often ones that are vectorizable. And integer ones are rarely vectorizable, but the intent is to keep elaborating the benchmarks to make them useful for the embedded computing, and I would think a floating point will give us that opportunity to use vector. Anybody else? Yeah.
Yeah. Sorry.
Oh, there's somebody at the microphone. Oh, sorry. Go ahead.
Yes.
It's the poet.
For embedded systems, there's a lot of platform details like address maps, interrupt vectors, and things like that. Could you say something on how much effort it takes to port the benchmark to run on a new platform?
So for these, the programs here, they don't have any interrupts or anything. These are very easy to port. People after we fixed a few bugs, have reported getting it done surprisingly quickly. For context switching, our idea is of writing a really simple assembly language program per architecture and just measuring that kind of trivially. Interrupt latency is going to be more complicated. It's kind of an aspirational goal, and we're looking for people to help us on that. But we know interrupt latency is important, and it's going to be more difficult. But we would now that you've successfully solved formal methods, we would love to have your participation in helping us with something like that. Okay.
So the question I have is, you list in a lot of these tests the standard deviation. I was just trying to understand what is it that
Let's say that again.
The standard deviation.
Oh, standard deviation.
So what is it that you use to get the variance?
How are we calculating it? It's the so-called geometric standard deviation. There's another word for it that I can't. A multiplicative standard deviation. So that's how we're calculating it.
So is it recompiling the code with different optimization seeds, or?
No, it's just like standard deviation from a normal distribution. Is not only do you supply the mean, you kind of supply the shape of the curve. So if you know that it's a very sharp point, so the mean's a very good. If you see 2 points, are these really different? And if there's a norm, if they overlap, then you say, well, these are pretty close. And the idea, if they're very steep and separated, then that's a significant difference. Okay, and this is good kind of benchmarking science, is to include standard deviations, even though people haven't done it yet. But that was the advice we got.